I'm not exactly known for my clarity of speech at times, but consensus is in on that one. All right, let's begin with a word of prayer. So, Heavenly Father, I thank you for these students, and we thank you just for another day to meet together and talk about your creation. Thank you that we can talk about it openly here. We have that freedom, and we just ask that you be glorified, Lord, in what we do this day. In I pray, Lord Jesus. Amen. All right, so the one known as Crazy Ball has maligned me into going back and deriving Snell's Law for you. If you're happy, Paul, let's see here, Snell's Law. Apparently, the impression was left in the last lecture that I was trying to make it seem harder than it needed to be, so I need to address these issues. Here it is. So the time it takes for some light ray or some, let's say light ray to travel should be the integral of dt, right? But that would be the integral of ds over v, because v is equal to ds dt, right? And I can recast that as the integral of 1 over the velocity as a function of x, all right? And then the square root of 1 plus y prime squared dx. All right, so this is my Lagrangian, which is so that's my Lagrangian. Here's a picture. We're thinking of x being like this and y being like this, and perhaps we've got some kind of interface. We say we've got n1 here and n2 here, and we're trying to derive the result, which is known as Snell's Law, that says if you have light going from one thing to another, one material to another, then it refracts, right? It bends at the interface. And so if this is theta, that's theta 1, this is theta 2, there's a relation between those angles and the index of refraction, known as Snell's Law. Okay, so derive it. So if this is f, then the Euler-Lagrange equations, partial f, partial x, partial f, partial y. What's partial f, partial y? Well, it's 0 because there's no y dependence, right? These new markers sometimes are not so good. And partial f, partial y prime is what? I get a y prime divided by v times the square root of 1 plus y prime squared. Why do I get that? Well, derivative of the square root, 1 over 2 times the square root, then chain rule gives me a 2 y prime upstairs, right? And then the other Lagrange equations say what? So we've got what? Partial f, partial, here a marker that works finally. Partial f, partial y is equal to d dx, because x is the independent variable here, right? Partial f, partial y prime. So what is that here? That tells us that 0 is equal to d dx of what? Y prime over v times the square root of 1 plus y prime quantity squared. So what does that say? That says that that quotient is a constant with respect to x, right? But I can re-image this, if you will, in terms of the angle, as follows. A little picture. So here's the picture I want to think about. So here's the theta, right? And so if this is dx, this is dy. What's dy dx? It's now I see why I had the minus tangent theta there. Well, I guess it's, yeah, I suppose, unless I take y, it's, well, fine. Minus tangent theta. See why I write that? Because the dy is, it depends on what we mean by dy. But if this, maybe this should be minus dy in terms of an actual, I don't know, plus or minus. You decide. It's some picayune, uninteresting sign convention discussion. Now Paul's going to mock me for this. Great. Now this has been ruined as well. I left a weakness. Now Paul will malign me for the weakness in this lecture. Here's plus tangent squared theta. I don't care. We're going on. Yeah, I told him to watch this one, so he was watching it. Crazy Paul, yeah, and he was giving me a bunch of static about the last lecture and lack of detail or something like that. And Crazy Paul, he was saying that the lecture was. He said I just phoned it in last class. I think it's. I'm kind of, and then I let him get under my skin. So here it is. Anyway, so. Okay, I met Crazy Paul as an undergraduate at North Carolina State University in the Eleazar computer lab. It's 24/7 computer lab that we would go and work at when I went there. It has a certain smell. I still remember it. It's just like Nam. No, I don't know anything. It was more like the smell of Indian food at 3 a.m. mixed with body odor. Some kind of superposition of those two things. It's timeless, that computer lab. Anyway, and then so I met Paul, and I learned various things about Paul, like his hatred for environmentalism, his belief in reincarnation at that point, a few other things. It was fun. So I can go on about this for several hours, so I should stop. So what is this? If this is a constant, right, you can rewrite this as, well, this is really tangent theta, right? And we'll take theta to be positive, all right? So this is v secant theta, because that's secant squared. And so what we have then, right, sine theta over v equals to some constant. But how do you define the index of refraction? N is equal to v over c. Oh, wait a minute, other way around. The index of refraction is usually greater than 1. So the index of refraction in the vacuum is 1. In air, it's about 1.002. Which means that the speed of light in air is slightly slower than it is in vacuum. Anyway, so if I do that down here, then this, of course, gives me what? Sine theta over c over v, c over n equals to constant, or simply n sine theta is equal to a constant with respect to x. So if you had a medium which the index of refraction was continuously varying, then this is what you would see the light bending as the n changed. But we usually just do problems in physics where we have two mediums, one of n1 and one of n2, and in that case this just gives you n1 sine theta 1 equals n2 sine theta 2, which of course is Snell's law. But this shows you how Snell's law is actually derived from a least time principle for light traveling between two mediums. Make sense? Is it? I just saw Lauren taking the tripod and going like this with the. Yes, you can. Oh, you got the last. Oh, I see. It was. When are you going to get the active cloak for your head so that we can bend the light around it and see the proper system of mirrors and some sort of active imaging? No, ducking is it's so 20th century. Oh, so here you go. Nerds for all of you, because I was grading your homework and it's awesome. I don't usually get to say this, but I just want to keep throwing them the joke, see how long.
I can keep doing this. I do this at work all the time. Woo!
Who's missing? Who's missing?
Yes.
Oh, I always have nerds.
Oh.
No, it was planned. Although I was going to give these to Calculus 3, but as I was creating your homework, Mission 1, I decided that, I mean, oh, you're feeling better. You're like, oh, Mission 1. Yeah, that was the one I did good job on. Don't spoil that for me. I don't want to know what happened in Mission 2. I'm not there yet.
Oh, I don't know what that. Get the nerds back.
No, if you guys had done what you did on Mission 1 in my linear algebra course, you'd all have A's. I mean, some of...
I don't have a grade in that class.
All right, so another example. Another quick example, simple pendulum. I think in your homework I gave you the double pendulum. If you really understand this one, it's not hard to do that one on the basis of this one. So length L, you have mass M attached to it. And so basically the problem is just to find the equations of motion. That's all we're going to do. I think that's why I say in your homework too is to find the equations of motion. I don't say to solve the equations of motion. That's harder. And so to set it up, basically you just have to choose coordinates. And so the coordinate I've chose to describe the simple pendulum is just the angular coordinate. All right. So here's a way you can do that. I need to find the kinetic energy, and I need to find the potential energy, right? So the kinetic energy, which we use T here, is 1/2 m x dot squared plus y dot squared, right? And the potential energy, U, is equal to mgy, all right? So let's see here, y is equal to L sine theta. No, wait a minute, is that right? Cosine theta. Sorry, eventually I'll learn trigonometry. Right. And technically speaking, let me just not write that. I should really say minus mg L cosine theta. Why the minus? Yeah, it's downward, right?
Where do we get T from?
T is just a letter. It's just kinetic energy. Oh, this is 1/2 mv squared. That's v squared. So, of course, x is what? X is equal to L sine theta, right? So over here, x dot is L cosine theta, theta dot. And y dot, well, that's L minus L sine theta, theta dot. So if you plug those in and square them, what do you get? Because we get sine squared plus cosine squared. So, okay, when you're applying the method of Lagrangian mechanics to a problem in physics, you basically have to look at the problem you're given, and you have to choose coordinates which parameterize the motion. I said for a simple pendulum, theta parameterizes the motion. Now I asked you guys a double pendulum. You have a pendulum attached to a pendulum. So there you want two angular coordinates is what you want to do. So just, a colossal hint for your homework problem, draw this picture. And your kinetic energy here would be something like what? Like the speed of 1 squared, the speed of 2 squared. So you take x and y for 1 and x and y for 2 and take their x dot 1 squared plus x dot 2 squared. Y dot. I don't know. I don't want to write it all out, but basically just do this twice and you need the potential energy for both. If you have two masses, you take the potential energy for both, add them together. It works that way, right? Okay, but what's the Lagrange equation here? Well, partial L partial theta is equal to d dt, partial L partial theta dot, right? Which implies what? 0. Oh, I'm sorry, not 0, right? What is L? I got too excited here. I forgot to tell you what L was. L is equal to 1/2 m L squared theta dot squared plus mgl cosine theta. So that, folks, is the t minus u. What was the question? So, oh yeah, so partial L partial theta actually does have a, it's not, theta's not ignorable here like it was in the last lecture. I actually have a theta dependence. Partial L partial theta is minus mgl sine theta. And then the other term is giving me what? It's d dt m L squared theta dot. So I can cancel the g and the L on both sides, right? Or is there a g? No, I can't cancel the g. There's only one g. Cancel the m, right? Yeah. And so what I get then is theta double dot plus g over L sine theta is equal to 0. So I can cancel an L, I can cancel an M, and then I'll just make the coefficient of theta dot dot, the second derivative of theta, be 1. Now, if theta is approximately 0, right, or in other words, if sine theta is approximately theta, which is true for 2 within a percent for like theta from 0 to 20 degrees, right? If you'd like to see the details, Paul, it's in my Calculus 2 notes. I explicitly calculated using the alternating series test on a particular interval. I even have a graph of this versus that and the distinction there between. Paul, let's see here. Sorry, I keep talking to Paul. Seems necessary though. G over L theta is equal to 0 in that approximation, right? And then for those of you who are currently taking differential equations, you can immediately go, I know what that is. I've got lambda is equal to, plus or minus I squared of g over L as my characteristic value, and so the solution is theta is equal to theta naught cosine of the square root of g over L plus some phase delta, let's say. So there's the actual small angle solution to the simple pendulum. I can actually solve the equations of motion here in that approximation because it's relatively simple. Now, of course, that's not the honest truth, right? Even in your lab manual in physics, they give you a formula for the actual period in terms of higher corrections to the sine theta formula. And so the period, in fact, is not independent of the angle. This is just, it appears that the period here is the square root of, I think I've lost a time, right? T. It appears that the period doesn't depend on the angle, but that's just an illusion of the small angle approximation. If you include higher order corrections, the period of the pendulum depends on how far it swings and everything else involved. Any questions?
So, how do you find potential energy?
Very good. So the way we find potential energy in these kinds of, so first of all, the assumption is that these pendulums are near the surface of the Earth, where the underlying thing is that the force of gravity is mg, where g is the constant 9.8 meters per second squared. So that is equal to minus du dy if we take y to be the vertical direction. And so that gives me this general formula, mgy. Oh, and I'm sorry, if I'm talking about gravity going down, I'm missing a minus sign here.
Okay.
So so for a single mass, it's mgy, right? If I have two masses, here's a popular example. So suppose I have a teeter-totter. I always found this example was instructive in terms of setting up potential energies for systems. So if I have a teeter-totter like this, and say this is L1 from the pivot point, this is L2 from the pivot point, right? Then maybe this is theta, right? And if the teeter-totter is straight, then I know that it's theta on the other side as well, right? Here's M1, here's M2. So the potential energy for this, so if I take this to be y equals to 0 for my convenience, because you can set the 0 to be 0 wherever you want. There's this invariance, this translational invariance that you have to work with. So I do M1, G, and then I just need what's Y1 here. It's L1 sine theta minus M2 G L2 sine theta, right? Because by the geometry, there's also a theta in here, right? So the basic thing is you find the potential energy for each mass in your system, and then just add them.
And so that's always true?
As long as we're talking about a problem where we're near the surface of the Earth, where the only conservative force at play is gravity, and we're using the approximation that it's constant, the force is constant, then yeah. So is it always true? No.
But like they can be connected in arbitrary ways.
Yeah.
It doesn't matter how they're connected, you just...
Yeah, potential energy, you know, put these things in a salad bowl and roll them around. Potential energy doesn't care. Potential energy is disconnected from those kind of dynamical constraints.
But it's different if you have different types of forces.
Yeah. If I have a spring force, then I need something else, like 1/2 kx squared. Or if I'm thinking about orbital motion, then the force of gravity is not constant. It's gmm over r squared, directed in the, you know, yeah. Now for your homework problem, I'm starting to show you, but basically got to do the same thing except for figure out, you know, pick where you want y equal to 0 and kind of, I suggest y equal to 0 is up here, and then you just basically put a minus on the displacement downward to each mass. So I pretty much already showed you what the potential energy for M1 is over here, right? I mean, this would be M1 G L1 cosine theta 1 would be for the first mass. But for the second one, you got to think about how you get to the you know, think about the coordinates of this being x2, y2, and think about how you would write x2, y2 in terms of this distance and the given angles. You see the x1 and x2 and y2 for M2 will depend on both angles, not just the first one, right? So that's what makes the double pendulum interesting. ¿Es bueno? Okay. Let's see if I have time. I think I have time for another example. Let me do it. So this time, let's take the pendulum and put it on a Ferris wheel. I mean, why not? Right? And we'll make it a relatively boring Ferris wheel. The Ferris wheel will be going at constant angular speed. Omega? 0. Well, we already solved that one over there. I'm disappointed in you, Joe. You didn't say 7.
It's not a I was talking about an actual number, not a variable.
Well, you could say it's 7, but 7's a variable. You missed your chance. Well, it's gone now. So here's my stupid.
You wanted a number, not a variable.
Here's my stupid picture of a Ferris wheel. And so, oh, it's not big enough. It's not big enough. All right, and suppose that this thing is rotating at angular velocity omega. And that's a constant. So I'll put omega sub naught on it just to be obnoxious. And then, okay, so the pendulum, I'm hanging a pendulum on the rim here. And so I'll put it a little bit higher so I can make a better picture up here. And so here's the pendulum. Right? And so this thing is rotating, right? Can you find the equations of motion of a pendulum that's stuck to a Ferris wheel rotating around with your first semester physics course? I think not. I don't think you have the theoretical framework you need to solve such a problem. And honestly, it might still be very difficult to actually solve the equations of motion explicitly here, but at least I can set up differential equations which describe the motion. All right? So you got to choose a coordinate that describes the motion. What should we choose as the coordinate that describes the motion here? I argue that this is one-dimensional. So the answer, well, I mean, there's no one right answer, but a convenient choice is just to use the angle off the vertical. So like over here, later, if the mass is, like over here, this is theta. Okay. Now, I'm going to assume that at time 0, here's where the the attachment point, pivot for pendulum here at t equals to 0, okay? The reason I'm saying that is so that I can say that this point right here is at what? It's at, and I guess I should tell you the radius of the Ferris wheel, right? Let's say it's r. And let's say the length of the pendulum is L, for lack of imagination. And so this point, the point of where the pendulum is attached, well, that has, that's what? It's R cosine omega t, right? R sine omega t, for the usual reasons. And I think we should make y equals to 0 the center of the, I'm essentially saying y equal to 0 is the center of the Ferris. I'm putting the origin at the center of the Ferris wheel for our convenience. So what's the coordinates here then? What's x and y for m? Mm-hmm. So you start with that point, right, and work from there. Yeah, minus L.
Oh, yeah.
Oh, yeah, plus L cosine theta. Oh, excuse me, plus L sine theta, right? And that makes sense, right? If theta is positive, it's adding. If theta is negative, it's subtracting. So that geometrically makes sense, the sign there of the SIGN, of the SIN term. And then our sine omega t, I think minus L cosine theta, right? Now here, R and L and omega are constants. I seem to have dropped my naught. If you don't mind, I'm going to do that over here as well, because it's annoying. Okay, so then how do you calculate the kinetic energy? Well, before we do that, what's the potential energy here? mgy, but that's mg r sine omega t minus L cosine theta. Now what's the kinetic energy? T is 1/2 mx dot squared plus y dot squared, parentheses. One half m. X dot is minus r omega sine omega t plus L cosine theta, theta dot, parentheses, quantity squared, plus parentheses, r omega cosine omega t, plus L sine theta, theta dot, parentheses, squared, closed square parentheses. So you see what happens. Something nice happens, yeah? When you square those out, let's see here, how can I say this? No, I guess those don't actually cancel. You end up getting something somewhat unpleasant. These terms, of course, give you r squared omega squared, right, from these terms squared added together. And then you get plus L squared theta dot squared. Those are, but then you've got the middle terms, right? You've got, I somehow didn't have a minus when I did this earlier. Is that minus right? How do you guys feel about that minus?
It's going clockwise.
This minus here in particular.
That's from the derivative of cosine. But if it's going clockwise, then those wouldn't actually be the parameters of the...
I'm assuming it's going counterclockwise. Oh, sorry. This is inaccurate. My formulas say that. You're right, though. You're absolutely right that my arrow was wrong, but I don't want to change that would, if I made my picture right and the formula is wrong, then I would make many corrections. Let's just fix the arrow. It's counterclockwise. That's counterclockwise motion. Yeah. Sorry about that. So this term, though, is that minus? I mean, where did that minus come from? It came from differentiating cosine. Yeah, I think I just made a sign error in my preliminary work. So if I with that, I mean, it's fine. It doesn't kill what I'm doing. It means I can't look at my notes. So this gives me minus r omega L sine omega t cosine theta minus r omega L theta dot sine omega t cosine theta, and then plus r omega L theta dot cosine omega t sine theta. So that's 1/2 m r omega squared plus L squared theta dot squared plus r L omega theta dot. And can you tell me how I can simplify that? That's actually sine of omega t minus theta, I think. Or is it? No, it's theta minus omega t, rather. So I'm using the adding angles formula for sine, which would give me sine theta cosine omega t minus cosine theta sine omega t, which is what I have. And there's a common multiplier in the front. So there you go. That's the kinetic energy. And so then, the Euler-Lagrange equations, partial L, partial theta, ddt, partial L, partial theta dot, give me what? well, partial L, partial, so again, L is what? L is t minus u, okay? I don't want to actually write it out. So how about, is there any theta dependence in the t? There actually is here, right? Right there. So that gives me R, L, omega, theta dot, cosine theta minus omega t. Is there a theta dependence in u? Yeah, there is. So it's minus mgl sine theta. Well, I get, okay, so this is equal to da 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 dot plus mgl cosine theta. Because the minus, I mean, I'm just the theta term here, right?
Minus u turned that positive.
Right. And then I get another minus from the differentiation of theta, of cosine theta. So there's three minuses. And then, so that's ddt of, I mean, it's just like the minus mgl sine theta we had in the previous, oh, I've erased it, but ddt of partial L partial theta dot, which has like what? Lots of stuff, right? So m L squared theta dot plus m R L omega sine of theta minus omega t. And I think I have an over 2 there. The 2 cancels here because I got a theta dot squared, which differentiates to give me 2 theta dot. But here the theta dot just differentiates to nothingness because we're taking the partial derivative with respect to theta dot. So that just goes, and I'm left with the 1/2 m RL omega.
From before, when we were taking things from like the squared, wouldn't there be a 2 in front of the second line from the bottom?
Oh, you're absolutely right. I should have a 2 on both of those terms. Thank you. So Daniel's pointing out that there was a 2 here and also here that I forgot about when I was squaring them out. And so that puts a 2 here, which is death to this 2. Ka-cha. Okay. Are there any other 2s that it... I suppose it puts a 2 here, though, huh? And there you have it. That's the other Lagrange equation for a pendulum that was swinging on a Ferris wheel going around at constant angular speed omega. And so you could, you could feed this to various numerical techniques that you know for analyzing differential equations and study the motion, for example. Or if you're very adventurous, you could try to solve it. I don't know. It might be solvable. This isn't too complicated a problem. It probably can be solved. I'm not going to try today. Oh no, I think Paul will shame me for not trying. I'm not trying to intimidate you into believing that you can't solve the problem. I'm merely stating that in class time we have a finite amount of time. We can only cover a finite number of examples. The mic will not pick that up, and thus will not aid Paul in having arguments from the gallery. Ha ha ha. You can say it louder. Please don't. Do you guys know what a fictitious force is?
What?
A fictitious force. Fictitious force.
Like,
It's not real.
like imaginary physics,
Like imaginary physics.
complex physics, let's do that.
More like well, here. So here's the method of Lagrange multipliers. Let me show you. So the idea of the method of Lagrange multipliers in here is basically you take the free Lagrangian and you add lambda times the constraint. And so let me show you an example of this. So in the plane, the free Lagrangian would be 1/2 m r dot squared plus r squared theta dot squared in polar coordinates, right? And if I want to put this on a circle, what do I do? What's my equation for a circle in polar coordinates? We could say r is equal to big R, right? I mean, it's kind of a yay circle. So this we would like to repackage as r minus r equals to 0. This is my constraint, all right? So the method of Lagrange multipliers for Lagrangian mechanics says what you do is you look at L, a different L, I mean slightly, I don't want to use a different symbol. Let me put a tilde on this one. Haha. Okay, so L is 1/2 m r dot squared plus r squared theta dot squared minus lambda. Minus lambda or plus lambda? Let me take a second here. Plus lambda, rather. Plus lambda times r minus r. So you introduce this lambda as if it's just another one of the variables, all right? So now this Lagrangian has a variable r, theta, and lambda, all right? And so you can look at, partial L, partial r is equal to d dt of partial L, partial r dot. And what's that give us? So we get, yeah, okay, I'll take that. You say what? R theta dot squared plus lambda, is that right? So this gives me the mr theta dot squared. You guys follow that? Equals to what? R double dot. Now, the Euler-Lagrange equations for the constraint, they're kind of silly. There is no lambda dot, right? So this is just 0. And partial L, partial lambda, well, that's r minus r. So in other words, the Euler-Lagrange equations for the constraint are just the constraint equation. So look at this here. This is very interesting. If r is constant, what's r double dot? Yeah, so this says that r dot and r double dot is equal to 0. So that says that r squared theta dot plus lambda is equal to 0. There's Nathan's head in the way. Thank you, Nathan. So lambda is equal to what? Lambda is equal to minus r squared theta dot. Oh, I have somehow juxtaposed the square, right? The square is on the theta dot. That's important. Mr theta dot squared, right? What does this mean? If you were constrained to going in a circle, right? In other words, your r is constant. What do you what do you feel? You feel like you're being you feel like you're being pushed off the circle, right? I mean, you have that so-called centrifugal force. I mean, but we know that the centripetal force is what's needed to keep you going in the circle, right? Lambda is precisely that centripetal force. See this? Theta dot. So if, let's see here. The other Lagrange equations for theta are what here? Any explicit theta dependence? No. So 0 is equal to d dt. Partial L partial theta is theta dot rather. Mr squared theta dot, right? That, of course, is the angular momentum. So L, or let's say J, equals to Mr squared theta dot. This is a constant. So what does this mean? If you rewrite, usually we rewrite theta in terms of the tangential speed. What's the tangential speed? How's it go? R theta dot, right? R omega usually. So if you rewrite this, that's minus mv squared over r. You should recognize that that's the centripetal force to go in a circle. That's an example of a fictitious force. It's a force which isn't a genuine force. It's a force which is a frame effect. It's just because you're moving in a circle, right? Is it really a genuine force? I mean, no. Not in the same sense as, say, gravity. So suppose you wanted to find the fictitious forces for a particle bound to a sphere. What could you do? Yeah, use spherical coordinates, right? Now, I should warn you guys, my notes have an unfortunate mixture. Some of my notes are using the physics spherical coordinates, which have the meaning of theta and phi switched. So I'm going to write down for you right now the Lagrangian in spherical coordinates, math spherical, okay? So we use what? We use rho, theta, phi, or I mean, well, however you want to order them. The picture, right, is, so if I'm at this point right here, this is, the distance out is rho, right? So this angle is theta, and this angle is phi. So one way you can derive the kinetic energy is to think about a little motion along that direction. So this would be like dl in the rho direction. Well, that's just equal to d rho. If you look at a little arc in the theta direction, so that'd be in the xy plane, it would be like along this circle, right? What's the radius here? Maybe it's helpful to have a picture. So more generically, this is rho, this is r, this is phi. So r is equal to rho sine phi, right? So this dl theta would be something like rho sine phi d theta. The green is in the xy plane. So you're sweeping that change in angle d theta along that radius, rho sine phi. And then the phi, the one that's swinging down like that, which would sort of look vertical here, so to speak. I mean, I don't know, you can, so dl phi, so that, let's see here, how can I say it? Well, here it so happens that the, on this particular point, r is equal to rho, so it's a little bit, but there are other advantages to drawing it here as opposed to up here. That's why I've made my choice. Anyway, if you draw the picture somewhere else, like up here, it's easier to see. that along, if you change phi, the dl phi should be like rho d phi. It has nothing to do with the other angle, the theta angle. So this is rho d phi. So these three infinitesimal displacements tell you that the kinetic energy, for the kinetic energy, rather the speed squared, if you like, in spherical coordinates, which is 1/2 m times the speed squared is kinetic energy. So what you're going to get is you got rho dot squared plus rho squared phi dot squared plus rho squared sine squared phi theta dot squared. So if you're just dealing with a particle, just a free particle on a sphere, that's the Lagrangian for it, right? And so if you wanted to find the force necessary for that, I guess to make this really interesting though, if I was thinking that I could derive the Coriolis effect here, but I realize now the thing I'm missing then is gravity. Because the Coriolis effect ultimately comes from gravity, right? So, that's what's going to be I mean, I can go through a similar calculation here, but it's a somewhat unphysical situation. It would be like, imagine you have a sphere floating in outer space, right? And you've got a ball constrained to that sphere. What are the fictitious forces that appear because of that motion? There's no gravity if I just say L is equal to T here. There's no gravity here, right? So, I mean, I can set this up. I just don't know what it means physically speaking, guys, what I'm telling you. Okay, so if I did this, though, if I did, that T, and then minus lambda times what? Times rho minus r, and then go through a similar thing to here, I would find that there's fictitious forces that appear based on both of the angular coordinates. But since it's not as physical as I was hoping, I'm just going to stop right there for this one. Any questions? Let me bring it back down to something like your homework, for example. Suppose you had, some surface, I don't know, x squared plus y squared plus z squared, and suppose that the force of gravity is minus mgz hat, so you're near the surface of the Earth, and you got some ball that's constrained to this surface, right? And it slides without friction, all right? So the only force involved is gravity, but you're stuck with this constraint. What you would do if you use the method of Lagrange multipliers, you do 1/2 m x dot squared plus y dot squared plus z dot squared, right? Minus mgz, except it becomes what? Let's see here. This is equal to minus du dz, so what's in this language? U is equal to what? Mgz, so yeah, minus mgz. Just checking on the sign. And then what? Then you do minus lambda. I guess I didn't finish the surface. It's x squared plus y squared plus z squared equals to 7 there. 7 is constant though. And so I would do, and that would then derive for me the Lagrange equations would give me the equations of motion that were necessary for that to happen, for the particle to be stuck on that sphere like that in Cartesian coordinates, yeah. And the really cool thing is the lambda has to do with the force. It actually has the significance of it has to do with it being related to the force that's necessary for that to actually happen. You guys seem tired. Do I need to give you more nerds? Unfortunately, I'm out. Maybe I need more nerds. All right, I'm out. All right, so what is left for us to do? What did I promise you guys last time? Do you remember, Lorenzo? Yeah. So I told you guys I would show you the solution to the central force problem. So let's look at that. What is the central force problem? So here's a picture. You have M1 here. You have M2 here. I'm going to leave it as an exercise to you guys that, well, let me shut up. R1, R2, all right, and then the vector that goes from one to the other would be, I would call it R1, 2, going from 1 to 2, and then M1's at R1, M2's at R2, R1, 2 is equal to what? It's equal to R2 minus R1, right? I'm going to call that just R, little r. And then the other thing we're going to use is the center of mass. So the center of mass, I don't know where it is exactly, somewhere in here, we'll use capital R vector. And so capital R vector is defined as 1 over M1 plus M2, M1 R1 plus M2 R2. It's the mass weighted average. Funny. It's essentially a weighted average, center of mass. All right, so the central force problem says that you got these two masses, and the motion between them is just it's responsible. Where is it coming from? It's just coming from some so-called central force. And so the central force just depends on the force just depends the magnitude of R alone. Okay, it's something like that. It's a central force. All right. So, but before we get more into that, so what that actually means, though, is that when we set up the Lagrangian, right, we can just say that U is U of R for the Lagrangian. The potential energy just depends on R alone. Now, I hope I've done enough today that you guys could easily set up the Lagrangian for this just in terms of like x1, y1, x2, y2, right? I mean, you could do that. What's the Lagrangian here? It'd be 1/2 m x1 dot squared plus y1 dot squared plus x2 dot squared plus y2 dot squared, close parentheses, minus u of r. Oh, I lost it. But before I do that, I need to derive just a little bit of relations between the little r and the R1 and the R2. So we have R is equal to R2 minus R1, right? And we have R is equal to M1 over M1 plus M2, R1 plus M2 over M1 plus M2, R2. I haven't really written anything shockingly different now. But here's the thing. You can do algebra, all right, straightforward algebra, and solve this to get R1 is equal to R minus M2 over M1 plus M2, little r. And R2 is equal to big R plus M1 over M1 plus M2, little r. So that is the positions of M1 and M2 in terms of their relative position and also the center of mass position. Okay? So once you know that, you can define the velocity of the center mass, big V, right, is dr dt, and you can talk about the relative velocity, little v. See, my big V has the little things on top, right? Little v doesn't.